Okay, linear approximation. Who did, ooh, that was fun. Ooh. Okay, so basically, the only thing to keep in mind is, one, remember this. I feel like that's pretty important, so just make sure that you remember this. And then the second thing to remember is that the x in this equation is where you are approximating, and the a is kind of the number that you know what the value of the function would be. So I always like to use the square root of 9 example. So in that terms, 9 would be your a, and let's say you're trying to approximate the square root of 8. So you know that square root of 9 would be 3, so that's your f at a. And then you can evaluate the derivative of the square root at 9. And then here you'll have 8, here you'll have 9. And then just one way to check it is that you want to know basically if this is going to be a negative number or a positive number. If, let's say in this case, 9 is, you know the value of the function, 8 is smaller than it, so then this should be negative. But then if it was 10, that should be positive because you're adding on to the value of 3. So the square root of 8 is less than 3. Square root of 10 is greater than 3. And that's kind of determined by the sign of this, which is determined by the sign in here. So that's just one way of checking over if you've flipped the x and a's, if you've kept them the same. Just make sure, oh, am I approximating the square root of 8? Should it be greater than 3 or less than 3? Greater than f at a or less than f at a? Any questions about that? Yeah? Okay, yeah. So the question kind of was if x stays as x. So this is the general form. So then let's say we'll use the same example. You want to approximate the square root of 8. So what's close to the square root of 8 that you know exactly what it is the square root of 9. So in that case, your x is kind of the point that you're trying to understand what the value is. So that's like the point you're guesstimating what its value is through this. A is the point that you know the value of the function at. Does that answer your question? Okay. So Taylor series. Oh shoot, not this Taylor, not this Taylor. Oh no, Taylor series approximation. Wait. She's a pretty big performer. Okay, so Taylor series approximation. It's definitely pretty confusing, but there's just a few things to keep in mind, and there's honestly really only 2 questions that they can ask you. It's like, give the Taylor series approximation of a certain function, or if you're given a Taylor series approximation, what is the second derivative, or what is the third derivative? And there's just a few things to kind of keep in mind. This is the general form. So if you look, what do we have over here? Linear approximation, exactly. So Taylor series approximation is just added on to that. You're adding more terms to become more exact. So this is the general form. All it is you take the value of the function. So if you just did that, that would basically be a horizontal line plus the linear approximation. Now you kind of get like the tangent line to that. And then you're adding on the second derivatives. You're getting closer and closer to what it is. So a few things to keep in mind is make sure you're dividing by this exponent's factorial. So don't forget that. And then also remember, this is the value of the function that it's like you know, basically. And then this is the value of the function, or the value of x that you're getting close to, so what you're approximating. Okay, so approximate does not start with a for some reason. It would be really nice if it switched. So yeah, if you were given a Taylor series approximation, and let's say the coefficient of the third derivative is 3. Make sure that you understand that, okay, so that means that 3 equals basically the third derivative divided by 3 factorial. So make sure you're able to understand kind of, don't forget the factorial. That's very important. So it's always the derivative, whatever, like second prime, third prime, fourth prime, divided by that prime number factorial, and then your brackets are to the exponent of that number, okay? So keep in mind how many asterisks are here, the same number here, same number here. Very important. So yeah, this is an example I came up with just kind of help understand what it is. If you imagine Taylor Swift music, right? Each term you add is like one new note or one new word to her song, right? So in Shake It Off, if you add shake to start, you know, you're like somewhat there. And now if you add it, you're getting closer to the actual song. If you add, what other songs like? Crazy, haters, no, gonna hate, right? Now you get closer. So each of these terms is a new word or a new note. And the more you add, the closer you get to the actual song. And eventually, if you add them infinitely, boom, you get the song. Does that make sense? That's literally, that's, okay, but yeah. Okay, so how does that look graphically? So I just want to kind of show what I meant. So here we have just shake. Okay, this is just one word. This is just the F at A. Okay, now we're going to add, boom, linear approximation. All right, it's getting closer to what the actual function looks like in red. Now let's add another term. Boom, it's getting closer. It's getting closer. It's getting closer. It's getting closer. And if I were to do that infinitely, I'll go back because it's kind of cool. It's really satisfying. So look, that's pretty close, especially near 0. We're basically spot on, right? So that's only like the 6th series, I believe. So that's essentially how it looks graphically and also how it looks musically. Yeah. Okay. Now, time for Maclaurin polynomials, or as I like to call them, Maclaurin polynomials, because it's way more fun to say. So from now on, I'm going to be saying Maclaurin polynomials just because I think it's a lot cooler. All right, so essentially there's 5 things that you should have memorized. Just make sure that e to the x, it's always going to be positive. 1 over 1 minus x, always going to be positive. And then sine x is going to be using the odd exponents. And then cos x is going to be using the even exponents. So the first term of cos x is 1, which is x to the 0, and then x to the 2. And then sine x and cos x alternate, so they start positive, then they go negative, positive, negative. Same with log of 1 plus x. It's essentially the same as e to the x, but there's no 1, and it alternates. Okay, so positive, negative, positive, negative. Just memorize these to the best of your abilities. That way you don't have to figure out what they are on the final exam. Any questions about these? If you're struggling with memorizing the polynomial expansions, there's another flashcard set that you can use to memorize it, help you out a little bit.